So thank you very much for having me here. So I think before we jump into the, let's say, the research thing, I think I would like to start with my short introduction. So born in Pakistan in 1988, did my engineering in mechatronics again from Pakistan. In 2011 and 12, I was in Germany and UK. Then the next year, I was found in Pakistan. After that, I again moved to Sweden and Spain doing the Erasmus Mundus joint PhD. And then last year, I did one internship in Rico Systems in Netherlands. And recently, I concluded my last internship at IPM Research, Japan. So let's see where this timeline goes next. But so what's this whole talk about is, I mean, it's a continuation of work, and to understand this work, I would also recommend you to look at the talk from the last year as well. So the context is that Apache Spark has a poor multi-core scalability, and what I did was that I actually tried to figure it out. What are the scalability delimiting factors which contribute to the poor multi-core scalability? And the first one is the work time inflation. Then you also find out that it's thread level load imbalance. Then you have wait time on I/O and GC overhead. And if you actually dig deep, that what is the cause of the work time inflation? It's in fact the DRAM bound latency. And then when I started looking at, okay, if DRAM bound latency is the problem, what kind of solutions you could do in the modern servers to actually hide that latency. And the first one is that you could make Spark NUMA aware. The other one is that to experiment that whether the hyper-threaded cores are effective or not. I also looked at the prefetches in the existing Intel architectures and found out that actually the next time prefetches, they are ineffective. And regarding the garbage collection overhead, what I found out that actually the choice of the garbage collection, it plays a huge role. And other thing is that how you are actually setting up Spark on the scale-up servers. Because generally, people do is that you have one bigger JVM, and then when it triggers the garbage collection, it takes a lot of amount of time. So what I recommend is that you should actually have multiple smaller JVMs, each one of size no bigger than 32 gigabyte. But that's one from the last year. So this year, I'm going to talk about what I've been doing since then, which is actually exploiting near data processing. And that's where the focus of the talk is. I call it the Project Night King, which aims at improving the single node performance of Apache Spark using near data processing architectures. And we have recently published a paper on International Symposium where we looked at the opportunities of these architectures for Apache Spark. If you want to read about other things, that's the 4 papers I also have, which is available on my profile, so you can read that one as well. So what is near data processing? I mean, the idea of near data processing is that you are actually moving compute to the data. I mean, the general way of doing things in the von Neumann architectures that you actually bring the data to the caches, and from caches you bring the data into the registers, and then in the execution units inside the cores you do the computations. And then you finally move the results back to the main memory or to the hard drive. But if, let's say, your workloads, they are bound by the latency, which means that you are doing a lot of data movement back and forth between main memory and the CPU cores, would it make sense to actually moving the compute units either inside the memory or inside the storage, or maybe a combination of both? That's where the paradigm of near data processing comes into the picture, that it's a mixture of or a combination of processing in memory and in storage processing. And when it comes to compute, so you again have a whole spectrum that what you could put in the logic. I mean, you could put simple instructions. You could have some kind of a programmable logic here. You could have some kind of compound instructions, for example, gather, scatter, mem copies. You could also have some kind of bounded operations as well. So that's the taxonomy of, let's say, computation in memory. But the question is really, out of all this spectrum, where should we focus on for Apache Spark? Should we go for bounded operations? Should we go for the programmable logic, maybe DSPs? What? And then when it comes to the non-volatile memory and its integration into the system, over the period of time, what we see is actually a tighter integration, which means that you are actually moving the non-volatile memories and the CPUs together. And it's a tight coupling of non-volatile memory, RAMs, and the CPUs together. And in the limit study, basically this nanostores project, what they showed is that for the IO-bound applications, the tighter integration of the non-volatile memory with the CPUs, they actually help in improving, let's say, the IO boundedness of the applications. And the question is, would, let's say, in-storage processing, which is actually a combination of compute units attached to the non-volatile memory and the combination of compute units attached to the DRAM, would benefit Apache Spark or not? So that's really the question that I'm trying to answer, that can Spark workloads benefit from such kind of architectures? So which means that you have this whole Spark runtime system, and then you have a host CPU, which is connected with a PIM device, and also it is connected with the in-storage device as well. So it means basically what you're doing is that in the current existing servers, you are just putting some kind of compute units inside either the hard drives or the SSDs, and also inside the DRAM as well. And then the question is, can these workloads benefit from this kind of, servers or not? And the rationale behind is that these kind of architectures, they can actually reduce the data movement. So if you have less amount of data movement, you incur less latency as well. So your latency costs, they go down. And the way to answer this question is to actually start looking at these applications from the perspective of near data processing. And when I say it from the perspective of near data processing, it means to actually characterize the workloads into the IO bound and the memory bound, and try to figure it out that which kind of NDP would match the characteristics of Spark workloads better. So for example, here on this side of the graph, I have the whole spectrum of Apache Spark applications, starting from Spark SQL, then you have general Spark core applications, which is grep, sort, then you have the graph applications, stream processing applications, and then the machine learning applications as well. And the important thing here to look at actually the CPU utilization and also the wait time on the IOs. And what you could see is that actually for these Spark SQL queries, they are most of the time waiting on the IO, and they have very low CPU utilization. So all these experiments are actually done on a full system, which means it is a 24-core machine. And on the 24-core machine, you have on average 10 to 15% of CPU utilization. Whereas on the other hand, when we look at the machine learning applications, for sure, I mean, there you have a mixture. Some applications, they have a very high CPU utilization. Some has a moderate amount of CPU utilization. And then, I mean, the wait time on IOs, they are not so big as compared to the ones around here. But these are the average values. What happens if you actually look at the whole spectrum of the execution time? So what we see here, for let's say, for example, for the grep, which is actually a filtering application, that overall, during the whole execution time of the application, you have this constant CPU utilization, which is less than 20%. And then you have actually almost 20% wait time on the IO. And this white is actually that your cores in the system, they are sitting idle. So even if you have configured Spark to use all the cores of of the servers, and practically your cores are only active for 20% of the time. Actually, even less than 20%. It's almost 10%. And then 20% they are waiting for the I/O, and then they're sitting idle. In the k-means example, which is actually a machine learning application, you actually see two different kind of phases. So you have a phase of low CPU utilization and high wait time on the I/O, followed by a phase of high CPU utilization. So this is actually the phase where you are actually sampling the data from your hard drives into the main memory. That's why here you have a high wait time on the I/O. And once the data is in the memory, and since it's an iterative MapReduce application, your CPU utilization, it goes quite high. And that's where you do not see this wait time on the I/Os. And if you actually look at the streaming applications, you see, OK, I mean, you have a very less amount of wait time on the I/Os, but the CPU utilization is quite high there. So what we can infer from this data, I think is this one here. That Spark workloads which are not iterative and have high ratio of I/O wait time to the CPU time, like joint, filter, and aggregations, they are ideal candidates for the ISP. And whereas the workloads which have low ratio and they're bound by the latency of frequent accesses to the DRAM, they are ideal candidates for the 2D integrated PIM. So I would go back to this slide here, where I would like to show that what is the fraction of the sustained bandwidth which most of these workloads use. And what we see is actually for most of these applications, they do not fully even utilize 50% of the sustained bandwidth which is available in the current DDR3 or DDR4 memories. So the thing with these 3D stacked memories is that their bigger benefit comes from this high bandwidth here. Okay, you also have a logic layer there, but the major benefit comes from this high bandwidth. But if your workloads here, they are actually operating in this region, which is actually the idle, the constant region or the linear region, actually going to the high bandwidth memories would not help. So only if your workloads, they are operating in the exponential region, that's when going to the high bandwidth memories would actually help. And what we show is that for most of these workloads, they are actually operating either in the constant region or in the linear region. So it means that at least for the Spark workloads, we do not need these 4x higher bandwidths which are now available in the HMCs. But still, what we see is that most of these workloads, they are DRAM bound here. So it means that data movement is still the problem. So what I'm showing that both from this graph and this graph, that we do not need, let's say, the high bandwidth of the HMCs, but we still need the logic layer in order to reduce the data movement. And that's where I'm saying about the 2D integrated PIM. And we also see, if you read the paper, we see a very varying compute demands for different Spark applications. And the question is that how you can match those varying compute demands. I mean, for some applications, it's 20%. For some applications, it's 80%. The question is whether putting 1 or 2 ARM cores in the memory would help or not. And I think it wouldn't help. And what I am suggesting and proposing is that we should have a programmable logic, which means actually the hardware accelerators in the DRAM and the hardware accelerators in the storage. But the question is, it is still a bit of a refined hypothesis how we can test this hypothesis. One approach is the simulation approach. I mean, generally, whatever simulator you take, whether it is Gem5 or some other simulator, generally they are quite slow. And when it comes to the big data applications, you need to actually conduct these experiments at the large amount of data, because the characteristics, they vary a lot at smaller data sets and at the larger data sets. What about the modeling approach? I mean, you can get some kind of overly estimated numbers, And what about going to the FPGAs and doing the actual development? Well, it's going to take a lot of time there as well. And the question is, could we combine a modeling and the partial emulation together to get some kind of estimates for this approach or not? And the question is that now in the current server market, we have tightly coupled servers as well, where you have, let's say, an FPGA attached to an Intel, let's say, CPU over the QPI interface. And the same thing you have from IBM as well, but the interface is actually different. So I think that, let's say, here I'm proposing a host CPU, which means that you have a processor there, you have a DRAM, which means you have a memory here, and then you have a programmable accelerators. You also have an accelerator here, and then you have an interface here and an interface there as well. So actually, I mean, this kind of, let's say, existing servers could be used to actually emulate these programmable accelerators near DRAM, these kind of, let's say, near data accelerators augmented servers. And the question is how you actually map Apache Spark on such kind of servers. So in Apache Spark, you have a worker nodes. So what you could do is that actually you could map these worker nodes on the CPUs, or you could map it completely to the FPGA. Or the third approach is that you could actually map it to both of these ones, which means that you actually offload one of the tasks to the core and one of the tasks to the FPGA there. And since it's a CAPI interface, so basically both of, let's say, these AFUs, or let's say the accelerators and the tasks running on the cores, they have coherent accesses to the main memory here, which is actually at the terabyte scale. But you also have some kind of a memory here as well, which has higher bandwidth, but it has much smaller capacity. And the question is, what are the trade-offs for these different mappings? And the next question also is, of course, what should we put here inside the FPGA? I mean, we are talking about Apache Spark applications. We are talking about offloading the tasks. So what should we put it inside the FPGA? And the fundamental concept underneath Apache Spark is actually an iterative MapReduce programming model, right? So you have the mappers, you have the reducers, and you have the shufflers. And since it's an iterative MapReduce, basically, once you have done all the reduction, you have a feedback, and then the next iteration starts. So basically, it is shown here. So now, the question is, can we map, let's say, this iterative MapReduce model directly into the FPGA or not? And the question is, how? So in Spark, we have a lot of machine learning applications. So all these machine learning applications, I mean, they have very different objective functions. And then you actually train them with the gradient objective functions. So they all have gradient objective functions, and then you train them with the stochastic gradient descent. So if you could actually map the stochastic gradient descent onto the FPGA, you could actually accelerate these different range of applications. And the assumption there is that actually the stochastic gradient descent is actually programmed in the iterative MapReduce programming model. And the same thing is also true for k-means as well, because the other class of applications is actually clustering. And the clustering applications, you could also program it in the iterative MapReduce programming model. So what kind of programmable accelerators I'm proposing is that you have actually a template-based design where you have the mappers. You also have the reducers. Then you have the hash-based shufflers. And then you have an on-chip distributed memory architecture. And then you have a finite state machine here. So for example, this interface, this power service layer, this is specific to IBM. And let's say these things, let's say these interfaces, they would change from architecture to architecture. For example, now in the CAPI, you have a power service layer. If it's HARP, they have their own service layer here. And if you have, let's say, some kind of high bandwidth memories, they would have their own proprietary controllers there as well. And basically, all these, how to say, these data paths, they actually support 32-bit floating point numbers. So what are the advantages of the design is that it is a template-based design to support generality. So which means that you could actually instantiate the number of mappers and reducers based on the size of the FPGA card, like how big is the FPGA. And then this general sequencer, which is actually a finite state machine, that's a tricky part here, because this one, its states can actually be varied to meet the diverse set of workloads. Because depending upon how you want to schedule the computations on the mappers, you could do that all just by either adding some states or removing some states from your finite state machine. And since the end users, they are, let's say, the big data engineers, we do not expect them to know the VHDL or Verilog. So we are proposing is actually that they use high-level synthesis, and they actually program the mappers and the reducers in the C and C++. And for sure, I mean, because of this, the very nature of the design, it supports the hardware acceleration of diverse set of the workloads. Now the question is that how we can show some numbers there. And for that one, I developed a roofline model for this server. So for that one, I actually used the time complexity per iteration of the Spark machine learning applications. So this one was actually used to compute the arithmetic intensities. And then this is the machine which is actually used to generate the roofline model. And from the previous experiments, what we know is that Spark has a poor multi-core scalability. So for example, if we look at k-means, so if you're actually giving it 24 cores, it flattens out at a speed up of 9 here. So this number is quite important. Now, I would actually map this number onto the roofline model here. So for k-means, the algorithm from its algorithm, the arithmetic intensity is actually 32. And let's say the peak gigaflops which k-means can attain in Spark, it gets here. So now what is, let's say, opportunity which is available for acceleration is actually this line here. And the assumption is that all the accelerators, let's say the accelerator design which I have proposed, it is accessing all the data from the system memory, which means over the CAPI interface here. And if you now change the assumption that this data, some of the data is actually stored in the FPGA memory which is attached directly to it, which has a higher bandwidth as compared to the CAPI, you also get another jump here as well. So it means that compared to the baseline here, you have this much of a potential which you can exploit from these kind of architectures. And for me, the rough estimates for this one here is actually 5x. For stochastic gradient descent, things look even better, because for that one, the arithmetic intensity line, it moves somewhere around here at 128. And then you even have a much higher potential in the stochastic gradient applications. But the question is that it's no free lunch, and it's not easy to just attain this one here. We have to solve certain problems to get there, and these are the challenges that needs to be solved, that how to design the best hybrid CPU and FPGA machine learning workloads, how to attain the peak performance on the CPU side, how to attain the peak performance on the FPGA side, how to balance the load between CPU and FPGA. I mean, since Spark, it's runtime system, you also have Java virtual machine as well, so how to hide the communication between Java virtual machine and the FPGA, and how to design the clever machine learning workloads using high-level synthesis tools. Now, this is also a very interesting slide here as well, because if you are talk to the people from industry, they would claim 20x, 100x performance improvement or acceleration with FPGAs. And what I'm showing is that actually by using high-level synthesis, yeah, you could get actually 20x, 10x. But the question is always, what you need to ask is that what is the baseline? Because if the baseline, it is not optimized, for sure you could actually get 20x. But when you actually put these accelerators again back into the FPGA, into the Spark runtime system and measure the end-to-end execution time, the speed up is not more than 1.5 to 1.6x. But if you want this 20x acceleration, I mean, you can do that just by learning high-level synthesis and Xilinx STSOC toolchain. Man, it's a matter of 3 months, and you could also start showing the same numbers there. And what I'm showing is that actually in these STSOC, you have different pragmas, which you actually insert into your starting code, which is written in C or C++. And so you could see that, for example, this is the baseline here. And as you, let's say, start playing around with the different optimizations, the numbers just start going down, down, down here. So these are the set of optimizations which are already available in the Xilinx STSOC. But what they do not have is actually the support for the MapReduce. And you could actually, what I'm showing is that by instantiating different number of mappers and reducers, you could even go further down there as well. So these numbers, this one and this one, they correspond to here, and this one corresponds to this one here. Okay, what happened? Yeah, I think I just have the last slide. Which actually the takeaway. Yeah. So if you want to remember certain things from this talk is actually that 3D stacked memories, they are the overkill for Apache Spark based workloads. You should look for the outcome of the project Night King, which aims at improving the single node performance of Apache Spark using programmable accelerators near DRAM and NVRAM. And conservatively, near data accelerators augmented scale-up servers, they can improve the performance of Spark machine learning applications by 5x. And never trust 20x speed-up claims which are being made in the industry, because most of the time, the reference points are wrong. And the Xilinx toolchain, it needs to support pragmas for the MapReduce programming model. And if you want to read all this one, I've just finished writing my PhD thesis. You could actually access this one somewhere in December as well. And that's my last slide. I would just like to thank Erasmus Mundus and European Union, which has actually funded this research. Thank you.